Alright, good evening, ladies and gentlemen. Non-binary folk. We're riding the Gemini cockpit on the Titan II to orbit today, and we're going to teach you how to rendezvous and dock. Without further ado, let's get this launch underway.
9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition.
Roger, we have nominal engine light.
Lift off. Roger, clock, Gemini. Yes, that's right. We got a roll program. Roger, roll. Good lift off, 8. Just like a good. We have a pitch program. Roger, pitch program.
Okay, so I'm sure all of you have seen my how to get to orbit video and how to come back. Now the Gemini is a little special in that it has a lift vector, and the craft from here on out are always going to be a little extra
Mark, 50 seconds. You're looking good, 8.
Finicky in terms of reentry. It's not this sort of ballistic reentry that Mercury used to have. Now, I trust that you all are intelligent and capable enough individuals to be able to start up this craft from cold and dark with the checklists provided. It's just a matter of finding the switches. I'll leave that all to you guys, since there are a lot of content in the trainings, but there is a lack of content in terms of how to necessarily do these more complex things like orbital maneuvers and this and that, and maybe you're interested a little bit in the physics behind it as well, and not just getting that STEAM achievement. And so these are things that we'll be going over in the course of today. We'll be rendezvousing and docking with the Agena, which is already launched on the Agena Atlas configuration. If we have time, we will depress and egress, and if we have time, we will do a deorbit burn. Of course, everything will be explained on the paint, pen, and paper, little MS Paint application we used last time. Now I might put those in because this is going to be a much more complicated flight. I might interrupt the flight and put those explanations in, and certainly if you just wanted to watch the flight. We got good light on Titan Stage 2. Of course, if you just wanted to watch the flight, I'll also, if I remember to do so, put the timestamps in for when the start and end of each of those whiteboard sessions are, and you can, of course, skip past those at your leisure. If I forget, just remind me nicely, and it will be done. They're not that hard to do. It's just a matter of remembering to do it amongst everything else I have going on in my life. So totally up to you whether you want to skip those segments or not. But yeah, if you're more interested, you might like them. So right now we're riding the Titan II to orbit, and we're just going to double check that OBS is recording this time, because last time it crashed. Super not nice of it. But it looks like we've got good stuff going on, and I'm going to check real quick to see if the OBS looks better with this light, and that does look like the panel is more readable on your end, and maybe this is too bright now, so let's try with the oh, that's the wrong one. Let's see here. The reflective probe on it makes it a little hard to read. I'll remember to zoom in whenever we're sort of looking at it so you guys can... How does that look? Yeah, that looks fine. That'll be okay for our purposes here today. We're not doing anything too complicated. We're just going to be doing home and transfer, rendezvousing, and docking. So at this point, we have the OMs to orbit capability. Let's toggle D-ring just so that we don't accidentally eject into space. And at this time, the level sense arm is uncovered, and the system is going to be running down on flight pressure now. While that's happening, let's take a look at our OBC cores. We're looking for current azimuth, target azimuth, as well as our current current perigee. All right, and we've got Seco. So let's get us separation here. All right, and let's just null our rates out real quick. Perfect. And we'll power down the propulsion until scanner has a lock. We'll move to the catch-up program. Everything up there looking good. Batteries off, squibs off. We won't be able to interface with the computer while it's loading, so we'll kindly wait for that to happen, and let's check if we need anything else after insertion. Safe, safe. Good, good. Yes. Those are already closed, it looks like. H2O and ohms. Good. Primary on Acme bias. Primary attitude drivers. Yaw. Primary pumps are on. Good. Antenna select adapter. Good. Off, off. Yes. AC power to IGS. We'll wait for the computer to actually fully load before doing that. We don't want to flip that while we're waiting for the computer to load, so we'll speed things up by skipping time. Right O2 bottle closed. Voltimeter to C. Left O2 bottle should probably also be closed. Alright, we've got a lock with the scanner. Computer's finished loading, so we'll flip to IGS. Good. Alright, so first things first, when you're getting into a rendezvous, you're gonna need to make sure you're at the same inclination as the target. So we'll look at our current inclination, which is 2891, and we'll look at our target inclination, 0289133. And you can see we've got the same stuff. Just to double check. 02891. Good. Alright. And now we'll look at our current apogee. 981221. And our current perigee. Now you can see there's a great difference between our apogee and our perigee. This means that our orbits aren't aligned. So right now, or sorry, not that our orbits aren't aligned, that our orbit isn't circular. So if I open up MS Paint here, let's get the big canvas going. Apologies, MS Paint is got this weird scale about it. Alright, so right now, if we look at Earth as that, and we trace our orbits, okay, right now, what's happening is in our, we draw out our anode and our dnode, in our ascent, we're coming up high, like this. We're coming down. And we're coming out, and we're really, really short. Right? So our orbit's this kind of weird way to one side. Now, let's say up here is our target vehicle. And we are anywhere on this line. Now, when we are closer to the Earth, we're actually going more orbits quicker than this object that's way out over here. So because of that, in order to speed up to the object, we actually need to slow down. So what we're going to do is we're going to do a small burn, a circularization burn, which is going to bring our orbit to be, relatively circular. And if I could draw, relatively circular, so it's going to look like this instead. And what this is going to allow us to do is it's going to allow us to orbit a lot faster and get in a proper phase where when we do this burn to expand our apogee, we're going to meet at the apogee at the same time. And it's absolutely imperative that the orbit is perfectly circular for this to happen. So we'll start with this maneuver right now. Alright. The way we do this is by going to platform and going to sharp and forward and allowing our autopilot to maintain sharp and forward attitude. We then go over here and we can request our circularization burn at our periapsis.
Roger, DCS.
And here's our pad. So we can see the purpose is periapsis circularization using the, this should say OAMS, OBC, not RCS. We have a time of ignition, ground elapsed time ignition of 1 hour, 11 minutes, 34 seconds, and 51 milliseconds. Our X, Y, and Z axes are listed here. This stands for -0, this is 0, and this is -714. We've got a burn time of 35.71 seconds, and our attitude doesn't matter because we are in the Gemini, which can burn in all axial directions. And we'll have a predicted altitude of 82.6 by 82.6 orbit. So, we're going to set our cryo selector to H2 so that we can monitor our power consumption and our propellant quantity to ohms so we can measure the amount of fuel we are using. We will now accept this DCS update, DCS standing for Digital Control System, and we can start the computer. At T plus 30 minutes, we can do a radiator temp check, and we're go for flow. So our time to burn is 8.2. Sorry, that probably changed. Hold on. Our time to burn (8.4) now. (8.5) is time to burn to finalize home and transfer orbit after 8.3 core burn. 8.3. 8. Time of ignition 8.4. Here we go. So it looks like we got 40 minutes on the clock. Just making sure that that reads 40 minutes. Yes, it does. Alright, so we'll get our event timer set up then. With 39 minutes. clock start. 57, 56, 55, 54, 53, 52, 51, 9, 8, 7, 6, 45, 44, 43, 42, 41, 40. Alright, looks like we're perfectly in sync. So we can turn off our ohms, and we'll go and skip time to our to a couple minutes to our burn. Okay, we're a couple minutes to the burn now. We're going to go rate command, and we're going to center out. Ignition. So we can see we're thrusting backwards now. For those of you who don't know, this is what the Gemini looks like. It's a solid vehicle, one of my favorites. And we're just going to make sure that as we're going along, we're keeping the rest of them zeroed out just by changing our attitude here. You can only burn in one axial direction at a time, so we're just going to be focusing on small attitude adjustments to null these other ones out as they appear. And we've got cutoff. We're going to check our map and make sure. And that looks like as good a burn as we can get. We'll let this reset back to 0. We'll reset the computer. Okay, so what did we do, right? If you look here, we've now completely circularized our orbit. So instead of looking like this sort of green and red circle, now what we're going to look like instead is a nice perfectly circular orbit around the Earth. Very good. Okay, so what's our next step, right? Our next step is going to be performing the Hohmann transfer burn, right? So now what's going to happen is, let's say that this here purple triangle is our target space vehicle. What's going to happen is we're then going to get a transfer burn so that our orbit can instead come out and actually intersect with the target vehicle. Now it's going to look a little more circular than this. These orbits are really hard to do on paint, so I'll just use the brush. We're going to do our burn, so we're coming out, we're intersecting, and we're coming back around, and our orbit's going to follow the same green line. Alright, and this is called a transfer orbit. So this is P1, phase 1, circular orbit. This is T, our transfer orbit. Okay, so here we've got phasing 1 maneuver and a transfer orbit maneuver. And then we're going to coast along until we intersect, and we're going to slow down. Because if we don't slow down, we might think, oh, we can dock, we see the Agena. Well, what's actually going to happen is we're going to very quickly start speeding up and fly way past the Agena extremely quickly. So we'll get to that part as we get there. But right now, we've just completed phasing 1. And now we're going to start our transfer orbit burn. Okay? So let's get Houston to calculate that for us. Rendezvous.
Roger, DCS.
Good. And we'll accept DCS. Let's double check everything. 222, good. 58, 57, good. 25. 26 and 27 don't really matter, they're just -0. It doesn't matter if it's -0 or +0. But just in case it does bother anyone, we can set them. Burn time of 70 seconds. And here's our predicted altitude. So you can see 160.9er, which is also the target apogee of the vehicle. So it's all coming together now. Same inclination, going to be the same apogee, and after that, it'll be the same perigee. And if you do it right, you should meet face to face. I can show you how to fine-tune that later, though, as we'll be needing to do that. This is wanting us to start our burn. Sorry, does that say 12 hours in? Really? 12 hours?
Roger, DCS.
I guess there's no way around it. $12, okay. So if that's the case, let's look at 19 real quick. Okay, so this will get us to 4 hours in. So around the 3 hour mark, we'll need to recycle our. Yeah, that's simply not enough. 12 hours. All right. I don't know if we'll have enough hydrogen in the tanks to do it. Oh, that's an annoyance. 06509 divided by 60 divided by 60. This will give us another hour at most. Oops, CO2 is building up. Sorry, cabin recirc. Alright, that'll hold us. It looks like we got just enough hydrogen in the tank. Alright, Alright, we've got 25 minutes to ignition. Ignition, or not ignition, clock start. Looks like the clock is 1 second late. That's okay. Should be good enough. Alright. Same thing as before. Maintain pro-grade attitude. Ignition. Alright, let's check. Perfect. 160.9 by 82.5. Okay, so where are we now, right? Right now, we are currently in our transfer orbit. We're right here, and we're coasting along. So, the next thing we have to do to rendezvous with our target is to perform another burn at the apogee and circularizing it out. And this will end us up in an orbit that looks like this, intersecting the two. And this is going to be known as P2, Phase 2. We're going to perform a phasing 2 burn. And you'll notice something funny, right? When our spacecraft moves around and it's here, you'll see that we're going to end up a little bit off, right? The orbit of this triangular vehicle is going to be the same, but it might end up not here, but it might end up a little bit ahead or a tiny bit behind. And so I'll show you how to deal with that when we get to that point. But first, let's do our phasing 2 maneuver.
Roger, DCS.
"37 minutes, counting down." We can go 38 minutes, actually. 38 minutes, counting down. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, start. Seven, 6, 5, 4, 3, 2, 1. Looks like we're in perfect sync. Great. So we'll perform the same maneuver as before. This time, 127 in our aft. Or sorry, we'll need to perform it going forward. Sorry, we're on the opposite side of the planet. Alright, we're 1 minute to the burn. attitude here. Ignition. Here's our Gemini spacecraft. Second spacecraft the United States ever made in cooperation with the McDonald Corporation. Same as the Mercury, McDonald. Apollo will be done by Northwestern. Let's take a look at our values, see how everything's faring along. Looking pretty good. Alright, so you'll notice we're about 0.1 nautical miles higher, which means we'll just be ever so slightly slower. Right? Ever so slightly slower than the Agena. So we'll get our encoder on, external lights to dock. For the time being, we'll cut the fuel, get our radar on. Alright, so you can see we're this far away, right? So at the moment, if we come back here to the paint board, I forgot to switch back to Reentry view. That's my bad. It's the same as the other burns. It's the same. That's crap. That's my bad. It's really the same as the other burns. Just make sure that as you're burning, when you open your map, your values are coming along nicely. As you can see, inclination's good, perigy's good, but our apogee is 0.1 nautical miles higher. That could be because of our mishap with the second burn. Or sorry, with the second burn, or as a second late, but that's okay, and it's good for our demonstration. Now we flip this radar on to see our distance and our range rate, and then we flipped on the encoder and the exterior lights. That's all we did. So the burn's the same as the rest. I apologize for that. That's my bad. Anyways, so we're here, right? And like I said, our object we're trying to rendezvous with is like it's over here, right? This is us. Agena's over here. So how are we going to go, right, closer? Because if we throttle up to get closer, what's going to happen is our orbit is going to get bigger. If we throttle down, our orbit gets smaller. Left and right, we push the orbit in inclination. Same with up and down. So it's a very delicate balance, because what we can do is we can actually say the Agena is over off to the left a little more. We can point straight at it and go towards it. But that changes our orbit. So in response, we need to look at the little needles, and we need to be doing small linear movements as well to keep our orbits the same. Alright, so let's show you how that's done. And it's absolutely imperative that I actually show this part. The other part was not that important. You've seen 2 other burns. You can pull off a 3rd one. You guys are smart. But this is imperative, because this is what gets most people when they try and get these achievements with Rendezvous and Docking. They always find it to be extremely difficult for no reason whatsoever. So, we need to move the computer over to Rendezvous. Alright, we're looking at the object now. You can see we're moving ever so slightly towards it, but it's very far away. It's some 20,000 feet away. That's almost as far away as an airplane is high. That's a lot of distance to cover, right? So we'll get our fuel activated again, and we'll show on the screens radar attitude. Okay? Now what that's going to do is that's going to allow us to point right at the Agena. Straight at it. So you can see it's about actually directly behind us. But you can see it's a little bit under. It's a little bit under the retrograde, or yeah, the retro attitude. A little bit under, and so because of that, our burn is going to change our orbit, right? So we can't see the Agena right now. It's far, far away. But we can actually use the encoder to help us see the Agena. So if we go over here, and we go over to the rendezvous checklist, and we go over, we can see that in here listed is 251 for acquisition lights. So 251. And there it is. That's the Agena, and we're in the same orbit as it. That's very, very good. So how are we going to get to the Agena? It's simple. We're going to look at it, and we're going to look straight at it, as we are now, and we're just going to thrust. Thrust forward. So you can see we need to slow down ever so slightly. But now relative, we're speeding up to the Agena because we're slowing down. Retrograde orbit, right? So the general rule of thumb is to never max out this, never go past this point on the needle. And as it drifts towards us, you can see that it's going slightly up. Visual or needles? I prefer the needles. So because we just changed our orbit, we also need to raise it now. We need to raise it. So it's going up, so we need to go up as well. And up looks like this. Just that one thruster. Up looks like that. So we're going to need to go up. So now we can see we're moving back into the regular plane with the Agena. Now that we're moving up, and eventually we'll need to start moving down a little bit and slowing down. And it's just this delicate balance. So now that our needles have crossed, we can do a little thrust down. Null the rates out. And you can see now we're very rapidly approaching the Agena. We were at 20,000, which is almost the height of an airplane, and now we're half that. And it's very important that you never let this range needle pass the rate needle. Otherwise, you'll smack into the Agena, and you'll have a very, very rough day. Real quick, let's keep an eye on core 19. And you can see core 19 looking a little pushy on that. So let's get it up to an hour 25 minutes again, and we'll request our retro at that time. Of course, we're not going to actually be retroing at that time. We're just extending our life here in space. So you can see it's going up again. We need to thrust up. It's coming back down, so we'll let it coast. And we're waiting for this computer to load, because the computer is not important for rendezvousing and station keeping. The computer is important for getting the precise docking attitude that we're going to need. We can cut cabin recirc now. You could keep it open if you wanted to, but I don't know. I like having to pay attention to CO2. It's just a me thing, really. It gives me something to do in moments like this where we have to wait quite an extensive period of time. So you can see it's drifting back up, and this is because we're traversing in our orbit further. So clearly we need to thrust up with higher acceleration. And you can start to just see the outline of the Agena now. Like I said, it's approaching very fast. And you can also see that it's ever so slowly drifting off to the left. So we can give a pulse going towards the left. Like that. Couple pulses, and we'll center those needles as well. Now this range needle is coming very closely to our rate needle, so we're actually going to take and we're going to throttle back a bit, just a little, not too much. Let it sit and recalculate. Like I said, we don't want to come smacking into the Agena, but now because we did that, look at us again. Our orbit has changed relative to the Agena, so we need to bring it back up, right? Look at that. It's changed relative to the Agena, so we need to bring it back up. And as long as we keep these two needles in line, we'll be able to rendezvous and we'll be able to dock. You just have to keep these two needles perfectly in line. You can see our rate needle has passed our range needle, so we need to slow down. Slow down. We need to thrust up and thrust left. Remember, we got to keep those orbits the same. Once we null our rate out to 0, our orbits will be completely the same again. So we just need to keep the air rate needles completely in the center, and we need to keep our range rate close to 0. Alright, so let's bring it back to 0 now. We're very, very close to the Agena. We can actually see it in the window. So as long as you keep these needles center like this, using only translation after your initial looking, you should only be using translation. Once you do that, you'll have a perfect orbit completely in sync with the Agena. And once it gets close enough, you can null your rates out. Right on 0. And our orbits are matching again. Now we can take a little thrust up, a little thrust to the left. And ain't she a beauty? Pulse a couple clicks forward. Again, just minding that orbit, keeping it the same, so that we can station keep. Another click up. 1 down. 2 down. And now it's just a matter of waiting for the computer to load. And you can see the computer's loaded, so we can run the computer program. That'll give us a digital range and rate. And we can go to the checklist here, and we can start the docking checklist. So we can go 250, 141, 201. 250, 141, 201. And now you can see we've got nice bright docking lights for us. We can see the docking port. We'll extend the index bar and we'll bus arm to dock. And instead of going radar attitude, we'll go computer attitude. And this is going to be the attitude we need to have in order to dock. So you can see we're going to need to very slightly move down a little bit. Now we can look at these needles again. Like I said, you only want to look once, translate the rest, right? So we can move forward and we can go down a little. Very slowly. Keeping these numbers 0. So you can see we need to move down. A little up now. A little to the left. 0 it out. Sixty feet. Time's looking like, alright, it's getting a little late, but we should have enough time for everything. 50 feet. We'll need to move a little up. 25 feet. 20 feet. Throttle down a little. Throttle down a little more. And capture. Now we can see Our orbits should be perfectly the same. This is a glitch. It's something I'll have to submit to Petrie. That's it's not good. So I'll take a screenshot of that. And now TDA control rigid. Bus arm safe. Exterior lights off. Alright, so should we egress? I think we could do an egress just for something entertaining, more entertaining than these orbital mechanics. Yeah, why not? Let's go for egress. Alright, cabin air recirculation. RCS heaters. Exterior lights. EVA bars. And vent. Suit temperature is looking a little uncomfortable. A little cooler. There we go. A comfortable 70, 73 degrees. Looks good. Alright, cabin pressure 0. Pulse. Orbit rate. Alright, and let's get out. So you can see, here's the Gemini. Thrust back. There's the Agena in all its glory. Take a couple puffs this way. And a couple this way. And we got ourselves some fuel. So a little thing that's not known about the Gemini is that the Agena target vehicle it was docking with the Gemini was actually going to be what was going to land us on the moon. That was the initial proposition. And so this they were testing a what was known as a Earth orbit rendezvous, basically launching multiple parts of a spaceship into orbit and having them all rendezvous in orbit to be massive, and then going to the moon and landing. This was before they developed the, of course, the lunar orbit rendezvous, which was the several smaller craft actually fitting inside the launch vehicle, the LEM, and going to the moon with the LEM and taking the LEM out and going down to the surface with the LEM, and this would save a ton of fuel and a ton of weight. So because it saved a ton of weight, it saved a ton of fuel. So this is sort of the less efficient method that we don't use anymore, and now we do everything sort of lunar orbit rendezvous style, which is pretty cool. And as you can see, this is the little handheld maneuvering unit, the HHMU. It's very crude, and the astronauts didn't actually really like it. It didn't really help that much. So they actually got rid of it in place of arm grab points and a tether. Well, they had a tether back in the other Gemini. We don't have a tether. We could go very far away if we wanted to. But that's not something we're going to be doing. I'm only out here to sort of just show you the impressive models that Petrie has made. Of course, you can also burn with this engine in Reentry, but we can leave that for another time. If at all, it's, not really important. It's something you guys can figure out with the checklists. You're intelligent people. Otherwise, you wouldn't be doing this kind of stuff. if you weren't. Not to say that people who don't do space simulators aren't intelligent. You know, everyone's got their niches, of course, like nuclear. But you know, this esque stuff. Like you wouldn't pilot a plane, you wouldn't fly in a spaceship. You know, these sorts of things. But yeah, I think that's long enough out in space. Very, very cool. So now let's sort of get ourselves back inside. And there we go. Close the hatch behind us. And we will do our post EVA. How much time do we have till retro? 32 minutes, 35 seconds. This is perfect, actually. That lined up very well. I'm surprised. All right. Let's say goodbye to the Agena. Rigid stop. Undock. Pull back. And forward. And let's begin our deorbit preparations. Oh, we lost battery 4. That's a rare occurrence. All right. What about our squib batteries? Well, we can't test them now, I guess. But we get voltage on C, voltage on C, voltage on C. Okay. We still got squibs, which is nice. Calibrator open. Should stop. Right hand O2 bottle open. Computer counting down. That beautiful, beautiful sunset. We've got 28 minutes to retro. Three 64 divided by 60 divided by 60. Okay, 20 minutes down to retro. 3, 2, 1, start. Okay. 19 minutes down to retro. $18. All right. 4 minutes, 16 seconds. Batteries are armed. Command Reentry. Ohms control and propellant off. Acme. Indicate retro attitude. RCS is on. Retro power is armed. Platform attitude high. HFTR off. Primary pumps off. Secondary pumps off. Radiator to bypass. Oh, we forgot to flow through the radiator. Oops. Oh well. Real quick, let's do cabin recirc while we get into attitude. There we go. We're going to start our 1 minute retro checklist now. Very shortly. Alright, we're down to 1 minute now. So let's maintain a 20-degree pitch down. SEP OM, SEP electrical, and adapter separation confirmed. Let's get back to that retro attitude. "30 seconds. Retro rockets armed. Auto retro arm. Eight, 7, 6, 5, 4, 3, 2, 1. Ignition. Retrojet is armed. Staging. Retro adapter jettison. for retro. Or ready for entry, sorry. Alright, 1430. Okay. And we've begun. Alright, now for simply surviving in Gemini during reentry, you just want to follow the instructions on the checklist until you see that message appear. Then once you start getting some fire and flames, bring it back to 0, like this. Once you get high acceleration, we're not there yet, so we'll go back. But just as a demonstration, that's about what it's going to look like. So we're just controlling our lift vector now. And we made it. Whew. Okay, things are looking fine and dandy. Rate of descent is chilling at about only 10 feet per second. That's very gentle, actually. 10.6 is coming up. And we've got 10.6. Okay, computer launch. Power off. Platform off. Rate gyros off. AC power off. RCS circuit breakers off. Okay. Only 300 or and some feet away from our landing point, which is pretty good. And splash down. Alright. Alright, so, what happened? Why were we able to control... Why were we able to control our reentry rolling? What was happening? Right? We could get closer, we could get further. Why were we able to do that? Right? That's what you're asking. Well, the Gemini looks a little bit... The Gemini looks a little bit like this. You've got your RCS, you've got your pod coming down, pod, RCS, RCS, and it sort of comes down and kind of closes off like that. So what's happening? Well, believe it or not, one side of the Gemini is heavier than the other, right? And so let's color that side in. Right, one side is heavier than the other. So you can imagine then that as we're heavy side down, what's happening is that air streams are coming in, they're compressing, forming these flames, and because one side is heavier than the other, it's sort of digging, so it kind of deflects air upwards like this. As it's digging down, the air is coming over the craft, more air coming over than air is going through the bottom. It's sort of, I mean, air is still going through the bottom, but there's a lot more coming up. And this is sort of pulling the spacecraft down like this. And so as it's compressing and it's heating with a large tilt in this direction as well, this spacecraft can control its descent as it's coming down. It's pushing more air over the top of the craft and compressing more down the sides here. Compressing, but more air is flowing over the top. And this generates a tremendous amount of G-forces that the astronauts are experiencing because of the compressive plasma being generated. Now let's say that instead the heavy side is over here on the top. So now what's going to happen with the heavy side on the top is the spacecraft is kind of going to be pointing more towards this direction and ever so slightly up. And so what's going to happen is instead of pulling down, instead the spacecraft, it's not going to pull up. It's just going to have more force the long way. And so because of that, because you're not digging down anymore, you get the even heating along the side of the spacecraft, even compression, as it's coming down through the atmosphere. And this allows us to sort of stretch out. It allows us to stretch out the duration of reentry, make it last longer, lessen the G-forces, but ultimately we'll miss our target because we'll take a quarter, a half of the globe to reenter. Now, we want our target to be somewhere in between these two, right? So we want the heavy spot to be hovering and rotating evenly between the bottom and the top and the side. What this is going to do is instead of leveling out our G loads and lowering them, having the heavy spot pointed towards the side of the spacecraft again is going to get that nice evenness across the spacecraft. But because the heavy point is more towards the bottom, we'll get ever so slightly more compression on the bottom of the spacecraft as it just slightly digs in. And what this allows us to do is this allows us to hold the G forces right where they are, and it allows us to gradually come in. And so instead of lowering the G forces and stretching out our glide, and instead of increasing the G forces to 9, 10, 11, 12, and fatal at 13 and burning up at 15, coming down and very, very steep, very, very hot, very, very fast, and sort of ending up before our target or after our target, we can keep spinning the spacecraft this way, and we can either hold it through and keep the spin, we can stop the spin, or we can have it slightly hang on one side a little longer by nulling out the rate and having it spin backwards in the other direction instead. And so by doing this, by sort of spinning one rotation all the way through, a half rotation, switching directions, spinning all the way through, we're able to sort of stretch and steepen our reentry path and our glide so that we can land precisely where we want to, as opposed to accidentally landing in Mexico or accidentally landing somewhere off the coast of Africa, which in Mercury was a big concern for some of these things. You know, you'd have the Mercury capsule coming down, ballistic reentry, 9, 10, 11 and a half Gs, coming down, and they had the landing bag because of this reason, because they were so worried they couldn't control their reentry that they'd smack into the ground, and that'd be very painful. So they had this landing bag, and they were worried about the astronaut coming out in this sort of metallic silver suit that they had back in the 52s and the 52 to 60 when it was the exact copy of the test pilot suit, this sort of metallic-y tinfoil look. They were worried that the people in Africa would come on and they'd be like aliens coming from space, when in actuality it was just the United States coming in, and whoops, we landed in Africa, or whoops, we landed in Mexico, or whoops, we landed in wherever. And so because of that, Gemini and Apollo have this sort of controlled reentry, and albeit it's not as controlled as say a space shuttle where you can precisely land down on a runway, but you saw as we were controlling our reentry, we were able to get 350 feet away from our recovery ship, and that's very impressive. That's a hop, skip, and a jump away. That's a 10-minute walk. So, the beauty of this is sort of control and lessening the G forces for the astronauts, so they didn't have to experience those high G forces of ballistic reentry and coming out losing 10 pounds in the process. And so this development was extremely important, and especially when we're coming in from the moon with these higher accelerations, 6, 7, 8, 10 times the speed of a bullet. You're moving at 300 incomprehensible speed. If an Earth orbit is 5 miles a second, imagine coming in from the moon where you've stored so much velocity. You're 250,000 nautical miles away from the Earth, you stored so much energy and so much speed that if you were to ballistically re-enter, you just get shredded apart, and you might even skip out and get in this highly elliptical orbit and die when your life support runs out. And so this was an absolutely crucial development for landing on the moon. And now that you know how to rendezvous and dock, and you know how to EVA, and you know how to survive reentry, now we can talk about getting to the moon and what that's going to take. So that's going to be very exciting for me to do. And we'll start with more of the basics, orbital mechanic-y stuff going on in reentry, and then we might move to something like NASP, where we've got more of the navigating, the cislunar navigation, translunar navigation, with the stars and the P52 IMU alignments, and we can start talking about stellar navigation and what it took to get to the moon with systems in the 60s that weren't very precise, and how they could tune their preciseness down to be almost exact and to control going to the moon without missing it and ending up in interstellar space, or missing it and ending up back at Earth with a highly elliptical orbit that now you can't control, or missing it and still being in translunar orbit. And so these things are very, very important technological developments, what we just did. And with our computer, we didn't have a computer in Mercury. We've suddenly got a computer in Gemini, albeit it's a ticker tape computer, but it's better than nothing. And in Apollo, we'll take a look at sort of what a electroluminescent computer relay computer looks like, and we'll get into how to operate verbs and nouns, how to operate a 16-bit computer, things that hate the number 6 and can't do any decimals. We'll learn how to operate that. We have 15 bits of information, 1 bit of polarity. So we'll talk about how they sort of worked around these things, and we'll start with reentry, do the very basics, getting to the moon, inserting cislunar and power descent initiation down to landing. We'll ascend, rendezvous, dock, get back, hopefully without dying. Apollo is very hard to survive reentry. NASP is a lot easier because it's more of a fine-tuned orbital mechanics. Reentry, just in its current state, it's 0.994. It's sort of still getting things worked out. The G loads are accumulating way too fast and stay too long for the types of rotations, and so we'll see in NASP, we'll see a picture perfect ideal reentry that's easier to control. And so reentry in its 1.0 phase will get these sort of things worked out, ironed out, and I'm not worried at all. Petrie is very open about these developments, and what reentry's development path is going to look like. And so I'm not worried that this will remain an issue, but right now it is an issue, and right now automatic reentry guidance is just not where it needs to be. It's planned for post 1.0 release for it to be fully functional, and so that's basically what's going to be happening in the near future. So thank you for stopping in. I apologize that the third burn, I forgot to switch back, but we did 2 burns. It's the same. It's just a little longer than the other 2. And so I apologize for that, and I'll try and remember to do the timestamps. So thank you. I hope you learned something, and have a good night.